Let's start with the principles of what is object code verification. Very careful here not to say object code coverage. The purpose is how to verify object codes and why do you need to do that. So objectives and activities, what are different approaches, and what is emission verification. So let's have a look at this piece of code. I'll give you 30 seconds to identify and think what this piece of code does. Hint here is that A and B are integer variables. And no, you can't just not simplify it to nothing. A bit of reflection, this is a function call in C, that it does some calculations with integers, and because these are not floating numbers, dividing by B and then multiplying by B effectively removes part of the remainder of the operation. So you would expect that if you write this piece of code, the compiler will generate straight line piece of instructions that would execute that calculation of the formula. And as you can expect, the fact that we put this example is that because that is not necessarily the case. So keep that example in mind when we go through the discussion. So given that previous example, we'll go to the tables in DO-178C, table A7, objectives A7-9. It says, verification of additional code that cannot be traced to source code is achieved. I'm going to go through in detail what is actually that meaning of that sentence. As you can see, this applies to DAL A only, and it needs to be performed with independence. What it really means is if the compiler, I'm going to repeat that many times, if the compiler introduces additional code that doesn't really map to the source code, because the compiler decided that I can do this in a different way, if you achieve 100% source code coverage, you cannot ensure, and because the compiler has done something else, that 100% of the source code also means 100% coverage of the object code. And because this has been a tricky objective, there have been quite a few additional support material, particularly in the DO-254C, we provide supporting information. We're going to go through that. Now, part of my job is to go and travel and see a lot of people and explain what are these objectives and answer the typical question. So we have a DAL A system, what do I need to do? And the comment we hear most of the time is to say, well, I need to do object code coverage, as if this was the only thing that the objective means. Now, we trace back, with our guess, that part of the confusion comes from the previous version of the DO-178C, that's the B version for Bravo, that suggests that the structural coverage can be performed at the source code. So the original text is on the right, and I'm marking two colors the 2 points we want to reference. So I know you can read, but it's very important to reinforce with emphasis what that text means. The text says the structural coverage analysis may be performed on the source code, and unless the software is A and the compiler generates object code that is not directly traceable to the source code. So that means that if your system is A and this code is not traceable to source code, then you need to do something else. Then you need to test that this extra code has been behaves correctly. And the verification part here means you have to add the right requirements, write some tests, execute the tests, and demonstrate that this code behaves correctly. And you then, using code coverage at the object code level, then you can say, and indeed, there is no other code that has not been exercised by tests. Unfortunately, there's a small side effect here. It could be that as part of running your normal source code coverage tests, if you then repeat the source code coverage at the object code level, you may cover this extra code that the compiler has introduced. And some people claim that this is enough to achieve the object code verification. Our strong belief, another interpretation, is that this is not correct. This is equivalent to what we call incidental coverage. You just happen, as a side effect of your normal coverage, to cover something else, but it doesn't mean that you satisfy the intent of the objective, which is, if there is code that has been added by the compiler, you need to make sure that you understand that code, find it, write some tests, execute the test, check that the tests are correct, and then demonstrate by coverage analysis that the code has indeed been exercised. DO-178C and DO-178C say something a bit more clear, but not much. But the principle is exactly the same. What it means is, for DAL A systems, you have to verify the correctness of any additional code introduced in the compiler. Repeat the same message. This is required independently of whether you do code coverage at the source code level or at the object code level. Again, the fact that you do object code coverage and you have 100% still doesn't mean that that extra code that the compiler has introduced really corresponds to some proper tests. And therefore, object code coverage on its own is not enough. And there is some notion of traceability from object code to source code. So if you have 100% source code coverage and there's a one-to-one mapping to the object code, then you can claim code coverage both ways. And this is what we try to highlight again on the actual text, which is independent of where the code from which you do code coverage, if your system is at A and the compiler generates code, then you would need to verify that code and check that this code is correct. And on the side effect, you need to get code coverage. Now, the main purpose of this session as part of our handbook that we have on our website, I really recommend that if you don't have access to the handbook on efficient software verification that we have made available, please go to our website and request it. It's free. It's a very valuable resource. We get a lot of very good feedback of how useful information this document has. So the objective of object code verification is not about object code coverage. The objective is about correctness of the additional codes. So look at the diagram on the right. If you have 100% of the code to be verified, and that's correct, then by implication that means that you would have 100% object code coverage. If you do not have 100% code coverage, you can certainly determine that you have not satisfied the 100% object code verification. But the implication in the other way is not correct. Some people would like to claim that just by having bottom left 100% code, somebody would say that just the right top here, that 100% code coverage implies 100% code verification. And I think this is a weakness on some of the arguments for certification. In some cases, and my colleague Matt Grom will talk later on, you can make that statement, but only if you know how the compiler generates code. And particularly when the compiler doesn't generate any additional code that you don't expect. So message number one, coverage cannot be used alone to demonstrate correctness, only that there is sufficiency of testing. Right. The other tricky issue is the comment that some people says, but what I need to do is I need to do source to object code traceability. Now, this is required as part of the object code verification. And this can be supported by tools, but not fully automated. And the reason for that is if you have source codes the compiler generates object codes, and in the process, it generates, when the code generation is really one-to-one, cross-references that says that object code line corresponds to that source code line, and source code line corresponds to the object code line. But this information is output as a debug information as part of the compilation process. It's probably okay, but it's not at the quality that you expect of a tool qualification kit. You do not have, in general, a certified or qualified compiler. So that information that you can derive from the compiler as to help you that object code traceability is not of qualification quality evidence to make that claim, unless you do then manual investigation or you try to qualify it. But good luck trying to qualify a compiler. So the issue number one is that you cannot trust by default that mapping. That mapping depends a lot on the compiler optimizations. This is why most people have very low compiler optimizations, but we see more and more people for performance requirements increasing the level of compiler optimization. And also, it hides the potential issue we mentioned before of incidental coverage, that you perform object code coverage and you just happen to hit piece of code added by the compiler, but you just don't know which one it is. So I'm going to now hand over to my colleague Matt Grum, who's going to go in deeper in detail about what is the typical examples of additional codes and what we can expect and the strategy of how to verify it. Matt.
Thank you, Guillaume. So there are a number of broad categories of where this additional object code comes from that doesn't necessarily correspond directly to the source code. For example, the compiler may insert calls to functions like memcopy, and I'll show you an example of that very shortly. There may be additional code that performs certain basic operations for purposes of optimization, such as division routines. Certain compilers, particularly ADA compilers, may insert array bounds checks and other checks that don't exist in the source code. There may be structuring. So, for example, sequences of long sequences of if, else, then else statements may be transformed into a jump table by the compiler. On certain languages, again, Ada and C++, there is a lot of exception handling that may get added automatically for you. Again, for polymorphic languages, you have dynamic dispatch for functions depending on the types which the function was called with. And that is code that, again, doesn't exist directly in the source code. Finally, there's a really important one, which is if you link to a library and the linker just inserts the entire library into your executable, even though not all of it is called from your source code. And this is important because people will often be thinking about their own source code that they've written and the object code that is derived, that is compiled from their source code. But it may be the case the linker's pulled in a library and there's functions in that library that aren't called, therefore that code doesn't trace to your source code, it's not been verified. And as a result, you have object code in the executable itself that doesn't trace directly to your source code. Ultimately, the object code itself is what you what you're flying, what goes into your production systems. So we'll start with a simple example here. This is a Compiler Explorer. It's a very useful website for showing you the source code, and you can see how different compilers will compile that. On the left, we have a function that takes a pointer and it's a pointer to an array of 100 characters, and it zeros that array. And when we compile this with GCC optimization level 2, you can see that there is no loop in the object code at all. We instead have a branch instruction, and we're branching to a symbol called memset, which is a function that performs zeroing of memory in a more efficient way than having a loop in your source code. So again, that is an example of object code on the right that doesn't trace the source code. In the source code, we have a loop, which implicitly has decisions and things involved in it. On the right, we have a function call instead. Now, what happens when we lower the optimization level down to 01? Now we get a much better alignment of object code to source code. It now traces directly. You'll see the code on the right on line number 6 in yellow. That is storing a 0 at a particular address. That's an auto-incrementing instruction. We then check to see if we've reached 100, the end of our buffer. If not, we loop back to label 2 on line 5. So that is a straightforward implementation of a for loop in the object code. Everything traces directly to the source code. There's no additional code there for us to verify. So now we're going to go to the example that Guillaume showed at the very start of the presentation, which is that we have some code on the left. It does some subtractions, some divisions, and multiplications. So we're going to compile that. I would expect to see some subtraction instructions, multiplication instructions, something like that. Here's what we actually get with GCC. Again, we get a branch instruction, which is a function call here, to a symbol called AEABI-IDIV-mod. So we've got some mathematical expression on the left, and we've got a function call on the right. What's going on here then? What's happening is the compiler has recognized that that particular expression evaluates to the remainder of, the modulus operation. So it knows it has a function to compute modulus, so it's just inserted a function call to its own inbuilt modulus function. The interesting thing is that, again, we're at optimization level 1 here, so let's reduce that down. We're going to recompile with 00. Now we get some stack frame operations that the compiler previously optimized out. But if you look at the yellow section, we still have the call to the modulus function. And this is even with optimization level 0. So this isn't something that's being done by the optimizer. This is something much earlier in the compilation pipeline. The compiler has identified what this particular formula means. And you can add brackets, you can shift it around, and it will still identify that. I've been trying to play around with the compiler options to see if I can turn this behavior off. And I haven't so far found a way of doing that. There may be an option somewhere that prevents this, but I'm not aware of it. It may be impossible for this compiler to prevent this behavior. There are still some general strategies that you can use to minimize the additional code. So the more you can minimize this untraceable object code, the less you're going to have to verify. And if you can eliminate it, then the verification objective doesn't apply. So number 1, the choice of programming language. So I mentioned earlier, Ada and C++ will have a tendency to introduce more object code that doesn't trace the source code on the Ada side because of lots of inbuilt safety checks. Not only array bounds checks, it will also, if you do a division, it will put an explicit division by 0 check in for you. Again, it's not in your source code, it will be in the object code. The choice of coding standards. So if you, for example, were to forbid certain code constructs that you know generate untraceable code, that would solve that problem. The choice of compiler, again, different compilers will behave in different ways with respect to this object code traceability. And the compiler options, as I mentioned, the optimization level can certainly directly affect how traceable your object code is to the source code. So in terms of minimizing it with compiler options, optimization level, as we've mentioned, smart linking, there may be options that allow the linker to remove sections or take certain sections of object code into the final application, so you avoid the problem of pulling in an entire library just because you've used one function in that library. Coding standards, so We've mentioned this, ADA compilers will do a lot of different things. You could, for example, forbid passing arrays by value to avoid copying them onto the stack. Again, that doesn't correspond to the source code. There are other ways of doing this. This will become clearer when we start to talk about the compiler verification activities in a few moments. So we'll talk a little bit about, so we've talked about traceability. This is how you establish whether or not your object code traces your source code, which bits don't trace. If you find that you have code that doesn't trace, then you're obliged to verify that code. So the DO-278C, which is the FAQ, which is a companion document to DO-178C, it provides some more further guidance of how to do this. First of all, before you can verify it, you have to establish whether it exists, and you have to complete this traceability action. Once we have that, then one of the approaches is to do what we've termed compiler verification. In simple terms, we just take pieces of source code, compile them, and analyze them and see what the compiler does. So if you were to go through all of the constructs that you plan to permit in your coding standard, compile them one at a time, examine the object code by hand. If you notice that there is object code that doesn't trace, then you can go back to the coding standard and make modifications. It sounds simple, but you have to take into account there may be combinations of source code constructs that generate untraceable code. There may be specific mathematical formulas, as we saw in the previous example, that generate untraceable code. So it's not a trivial activity. It's not just a case of going through every keyword in your language. You'll have to think a little bit more about it and design more rigorous testing to establish what circumstances cause this untraceable code to exist. Another approach is to simply examine the final object code. So you compile your application, you've got this artifact, an executable image. You can check that to see if any of the instructions it contains don't trace the source code. It's just one sentence in DO-274C that says, just examine the target object code build. But as I hope you can imagine, it's a non-trivial, it's a sizable activity to go through the entire binary instruction by instruction to check that it all maps back to the source code. So what do you do if it isn't directly traceable to the source code? Then it says you should perform additional verification, and then it helpfully says we're not going to address how to do that. That's up to you. So the two methods outlined here is this sort of pipeline of how the compiler verification approach would work. So we identify the compiler and the constructs that we plan to permit in the coding standards. We design a series of tests that are going to compile some code, examine it, check the traceability by hand. You can then go back to the start if you discover there are problems. Well, let's change the optimization level, let's change the coding standard, repeat the process. The key thing is once you've done this, once you have a compiler version and a coding standard, you can reuse that. So you know that you don't get direct traceable code. You can reuse that across multiple projects. In terms of the target object build verification, the approach to here is you go through all of your normal development process. At the very end, you have a candidate executable image, and you analyze that for traceability. The problem with this approach is if you then discover separately that you need to change a line of source code, you'll then have to go back to the very beginning and analyze that executable image again. And of course, you do that for one piece of software. That's not very reusable. You're putting effort into something that that is only going to be used once, essentially. So to summarize that, the compiler verification can be an expensive one-off effort. There's a lot of work up front before you really even start the development. There are advantages to highlighting these concerns earlier in the development lifecycle. You can make some intelligent decisions about whether you want to make your verification life easier, but at the expense of writing your software and the development more difficult. As a trade-off you can make with evidence there. But again, you get to reuse all the effort you put into compiler verification is reused across future projects if you keep the same or at least similar compilers. The target object build analysis. First of all, you can only start that once you've actually developed your software and you have that artifact. So there's a high cost to making changes. You have to get back to the beginning of the life cycle. You may find that there are code constructs that are difficult to analyze. It's difficult to determine where this object code came from. It's easier in the compiler verification side because you're dealing with smaller parts. So compiler verification, you take a small piece of code, small fragment of source code, you get a small fragment of object code. The traceability is very easy. If you've got a long chain of instructions, it can be harder to trace those back to the source code. And we have to repeat that analysis every time we change the code. So it may be a smaller effort for a particular project, but it's not reusable. So in practice, the compiler verification approach on the left is by far the most popular in the industry. Is there a third option there? So this is a hybrid approach that we're hypothesizing here. So the compiler verification is expensive, but the object analysis is not reusable. The build analysis is not reusable. You don't have to do it all in one go. You can work on verifying the compiler to reduce the untraceable code, and then a bit of manual analysis for anything that doesn't fit. And you can iterate this as you reuse the same compiler and as you reuse the same options across. Sorry, if you reuse the same compiler and you reuse the same coding standard across different projects, you refine it each time and do more of the compiler analysis approach, less of any manual analysis of bits that you are aware of need to be covered with manual analysis of the executable build. So moving on to the final point of how do we verify that additional code. So we're at the stage where, for example, let's say we've done the compiler verification, but we know that certain constructs are going to introduce additional code. We can't eliminate it. We've gone through all the process of can we eliminate through coding standards, through compiler options, can we eliminate this untraceable code? If not, DO-178C says you must verify this. Verification means proving this is correct, and the way that you do verification of software in DO-178C, source code or object code, is to write requirements-based tests. Sorry, you write requirements, you write tests from those requirements, and in order to check that your tests fully match your requirements and your implementation fully matches requirements, you should end up with 100% code coverage. And this is where this whole coverage is not correctness comes from. Coverage is a metric that tells you how well you're performing your requirements-based testing process. So if all of the code matches a requirement and it tests, and there's a test for every requirement, then you should end up with 100% coverage. So your tests should execute every single piece of code. So how do you set about applying the DO-178C requirements-based testing approach to object code that has been written for you by a compiler? So two sort of approaches that we're suggesting here. first of all, we need to specify what the object code does somehow through requirements. And the two approaches are the idea of requirements templating or adding explicit derived requirements. So I should explain a little bit what I mean by requirement templating. That's not a standard technique, but the idea is to start writing requirements from a template that can include language that will automatically cause you to generate tests that test the extra untraceable code. So to give you a concrete example of this, refer back to the ADA language, which when you do an array index, it will add an extra check to see whether the index is within the bounds of the array. So effectively the object code there will be some sort of comparison on the index. Is it greater than the size of the array that the compiler knows? If so, regenerates an exception or something like that. So if you were to have a template for your low-level requirements that specified that there should be array checks, there should be bounds checks on arrays, that will call you to write tests that will check whether or not you have, will check an inbound array index operation followed by an out-of-bounds index operation. And therefore, you implicitly have test cases that are testing and verifying the additional code. The reason we suggest doing this in a template is because the compiler will generate the bounds checks every time there's an array index. So you want some mechanism that means that every time you write a requirement that involves an array index, you include the language that causes you to write the tests, calls you to generate these two test cases in inbound and outbounds. The other approach is just as a more ad hoc thing where you add derived requirements where you know the extra untraceable object code is. So again, using the array index count, any function that you have that does an array index operation, you add a derived requirement. So it's a derived requirement because it doesn't follow directly from the high-level requirement, but it's something that has to exist in order to implement that functionality. In which case you will have an explicit requirement, and then you will write a test case for that requirement, and then you will measure the coverage you get from running those tests. And it's exactly the same approach with source code level requirements-based testing and coverage. You measure the coverage. If you have gaps, you go back to the process to examine whether you have missing requirements, whether you have code that shouldn't belong there. And in some cases, you may need to justify the coverage gaps, just like with source code coverage. Coverage by analysis is an acceptable means of achieving that. There are people and tools that promise an automated approach to object code verification. So one of the ideas that we're trying to really clarify in this presentation is the idea that a tool that measures object code coverage is not sufficient for meeting this objective. You can't simply say, we ran our tests, we ran our source code level requirements-based tests, we've got 100% object code coverage, therefore there is no object code that doesn't trace to source code. And you can't say that because you haven't manually analyzed the code to see if it traces, and the fact you've got 100% code coverage could be by accident, incidental coverage. So object code coverage isn't enough. It doesn't mean that it's not valuable. Object code coverage can be used as proof that you've done the verification right by writing requirements and tests. Source code object code traceability can't be automated at the moment. As Guillaume mentioned earlier on, the compiler will provide you metadata that will map each assembly instruction back to the source code, but it's really more of an association than a formal traceability analysis. And the reason the compilers give you this information is to facilitate debugging. It's what allows you to step through a compiled executable in a debugger and see the source code that is being executed. And if anyone has tried stepping through optimized code in a debugger, you will know that the source code it shows you is sometimes nonsense, because as soon as you start optimizing, the one-to-one relationship between source code and object code can become obfuscated very, very quickly. And finally, the reason we can't just tool optimize away this whole objective is because if there is this additional code, it has to be verified, which means you have to write requirements, and you can't generate the requirements from the code. The requirements have to come from some human understanding of what the code should be doing. You can't generate tests from code, because if the code is wrong, then your tests are wrong. So automation, although it's not a complete solution, it can support this verification activity. So coverage analysis, the source code level and the object code level supports this activity. The compiler, as I mentioned, can help you, can suggest the traceability, but it's not a qualified tool. The traceability it provides is more of an association to support debugging. It's not designed for this objective at all. Finally, if you have a tool which will allow you to record justifications, which are basically a structured and controlled way of applying reasons to any coverage gaps, such a tool can help you with the sort of bookkeeping, so that you know that eventually every coverage shortfall has at least been analyzed and understood. Finally, we just wanted to show you a screenshot of the Rapita 0 tool, which is a tool that Rapita Systems have for measuring object code coverage. It will show you the coverage on the object code as measured directly. So what you see on the right-hand side is the ground truth. This is exactly which instructions were executed on a particular trace run, a particular test run. And on the left, you can see we've applied the compiler the compiler mapping to try and indicate the source code coverage that corresponds to that object code coverage. It's also worth stating that although object code coverage tools such as Rapita 0 aren't in and of themselves a solution to the object code verification objective, that only applies to DAL A. If you have a DAL B or DAL C system, then Rapita 0 could achieve the code coverage objectives in DO-178C. And finally, you might not be following DO-178C. You might be following a different set of guidance, which may mandate object code coverage for a different reason. And the tool exists there to measure object code coverage for you. Finally, I'd like to hand over to Guillaume to summarize and wrap up.
Thank you, Matt. Very useful. So we're coming up to the end of our presentation. There's a couple of additional reflection. I just took some notes as Matt was talking. One of our philosophies or recommendations in achieving software verification objectives is to plan early and get the things right from the beginning, because it is well understood. We have some data we can share with you if you want, of what is the cost of changes the later you are in your software development process and verification process or certification process. So imagine the case where, as Matt was saying, you have finally produced the final object codes. You try to do this activity of inspection and identify that because of the compiler options that you use, there is a strange code that the compiler introduced. So what you need to do in that one is you need to go and change the compiler options, which can then imply having to rerun all the tests, because now you are generating a full code base which is completely different. So an early de-risking activity, and we even know some people that do all of these de-risking activities before SOI 1, so that whatever plan they decide to use, which means which compiler options you're going to use for your compiler, are already fixed at that stage. And then from now on, you know that there's no changes going forward. Right? Another clarification on the example is introduced before on the call to the library function is that, let's say that the library function call that the compiler introduces has two modes of operation, depending on, I don't know, if one parameter is positive, you do something, one parameter is negative, you do something else. In your code base, for example, in the case that we introduced, it could be that A and B were always positive, which means that when you do the object code coverage, the library function will have a piece of code that has not been covered at all, because all your tests are only for positive numbers. So the implication of this compiling to this code is that the generation of the code may bring in another piece of code that then ends up having dead code. And for DAL A, that code needs to be removed. And then becomes an issue if you don't have access to that source code. Or then you'll need to have extra tests to show that if you exercise the code or with the same negative numbers, you get the right outcome, or for example, you don't trigger division by 0. Okay. Another thing that came to my mind when we were talking about this is, but why do we do all of this? What is the potential defects that this verification objective introduces? So if you look again back to the example, the linker may bring in the wrong library. How do you know that? You may actually test your code with some example, because that's what it's supposed to do, but by importing the wrong library and therefore bringing in a whole other bunch of stuff that is on that library, you may be introducing a piece of code that could be accidentally be executed or is dead. So the principle of you fly where you test, you test where you fly means that every single object code assembly instruction used by the compiler in the final binary has actually been tested and therefore covered. Another comment on the sampling is that some of the practical approaches with some of the DAs is that, well, you don't need to really go through the whole 100% of your object code. You would be asked to do a sample, and that sample identifies where, for the construct that you use, whether there are any unexpected things. And if you have a strong argument that you already have constrained the compiler options and the coding constructs, it means that you're not going to find, hopefully, any issues. If you do, then you look a bit more, and then if you keep finding them, then you need to go back to the point. But the key part is that how do you know that the next time you do another builds, the compiler now, because of the extra code that you introduced, has not performed additional, has not introduced additional code, and now this one is the problematic one. We did a very interesting compiler verification activity for one of our customers, and what was one of the outcomes of the work is that we found about 20 issues on a significant piece of code. Most of the issues were strange behavior generated by the compiler that was functionally correct, but it resulted in a philosophy of generating code that was not safety critical. So the compiler verification activity, it is not only for the exercise of introducing object code, but whether the style of code generation was correct. And I'll just give you as a snippet of information for you what that means. There was the code base was in Ada, but that could happen in any language. And function pointers are not recommended unless you declare as initialization that you declare that particular code happens to be to that particular function. And because it's done at initialization stage or at compilation stage, the compiler is able to resolve that indeed that call corresponds to that particular function. The safety culture in that organization is that you don't trust your memory, the data, but you trust your code, because the code is a non-volatile memory, therefore it cannot be disrupted. Which means that the checking the sanity of the data every time you enter into a function and before you throw it away or before you return is a good way to say, I can trust the data because I checked that it's okay. I can trust the control flow because the control flow cannot be changed because my code is on non-volatile memory. Except that in the same conditions, the compiler ignored that this function point allocation could be resolved, and indeed it generated a call through a function table in the middle of the code. To reflect what this means. This means that there could be a single bit upset that could change that table, and halfway through the code, you just jump somewhere else or nowhere. So the compiler verification is something that then verifies that not only the code is correct, but it also follows the safety culture and then verifies the assumptions that underpin the safety argument of the code that you generate. A final reflection is, yes, code coverage at the object code level, together with code coverage at the source code level, also has some value. So imagine that use case. You have all your requirement-based tests, and you have 100% code coverage at the source code level. And you know that every single line of the source code has been exercised. Then you repeat those tests, and you do object code coverage. And you find some gaps. Straight away, you have now found code doesn't trace to the source code. So these ones, very easy to find. What you cannot make the claim is that there isn't no other piece of code in your code base that doesn't trace to the source code. But at least this segment is already been identified quite nice and quite clearly. So that is the end of my reflections. So what have we addressed today? Message number one, object code verification is not object code coverage. And finally, love, there is one question on the chat specifically as this, so we'll address that in a moment. Object code verification is there extra code introduced by the compiler? Need to find it, need to verify it, test it, and show that I cover it. And this extra code can be range checks or actual codes that actual instructions, or calls through library functions that doesn't belong, and therefore it is the extra code that belonged in that needs to be fully verified. This additional code comes either from compiling to this code or third-party libraries, and the way to do is either you do the work up front and do a compiler verification and you do it once, or you need to inspect the code and you repeat it multiple times. Or in some very clever approaches that we see some of the customers, you just don't do it. Because you know beforehand that the way the compiler works and your previous compiler verification that you did years ago guarantees that the compiler will never introduce that extra object code. So in some cases, with a good planning, that objective can be very easy to satisfy. In some other cases, it can be catastrophic. We have a particular story of a use case is a model-based code generator, where the model-based code together with the compiler generates so much extra code that the task is unachievable. So the idea in principle of doing automatic code generation for models and then compiling it has become an absolute nightmare for the final verification later on. We are a tool vendor. We have a solution for object code coverage, as Matt says, called Rapid Cover Zero. But we want to really make sure that we deliver the right message. The proper educational message is that if you are a hammer, not all problems are nails. In that case, it's a screwdriver. You can use a hammer a bit, but really you need a different set of activities to put it in. What I'm really trying to say is that I think it's negligent to push a incorrect statement just because we just happen to have the tool. The tool does help a lot. Tool Rapid Cover 0 achieves object code coverage and it can help you as part of the verification activity as an object code coverage. We have testing tools that allow you to write tests and inject tests to that particular step, which is called Rapid Test. But the key important here is that the intention of the objective is, can you trust what your compiler does? Remember, you shall not trust anyone, even less the compiler. The objective here is, can you trust the compiler? Show me that you have some confidence. How much additional code is typically added by a compiler? Does this depend on the programming language?
Yes, it very much does depend on the programming language. C is kind of well behaved in this regard. It was designed originally to translate very directly into object code. That's why you have the ++ increment operator in C, because the machine that the architecture that it was developed for had an instruction that did that, and it all maps directly through. There are some weird cases as compilers develop and they get better, such as the divmod example. So there isn't that much with C, especially at lower optimization levels or at O0. Ada and C++, there's a lot more, because you've got the whole the dynamic dispatch at runtime, and Ada has all sorts of arithmetic checks and bounds checks.
On that note, typical question that people ask is, oh, we're using C++ because our programmers like it. Except that what makes the life of the developers easier and nicer can be an absolute nightmare for whoever needs to verify the additional code. So some of the recommendations, which is not our recommendation, but is what we learned from the customers who successfully got certification, is to consider the total efforts of development and verification. And sometimes making the life of the programmers, I don't know, doubly difficult of having to write code in a very restricted and constrained set of programming guidelines may make the verification activities further on much more easier. Now, related to that question is another one that we very recently somebody asked us, which was, we are using a third-party library to do some numerical computations for whatever we do, but we haven't developed that piece of code ourselves. So the piece that we control does really follow some very strict coding guidelines, and we do a compiler verification or sampling. I mean, they are okay. But the impact of bringing in a third-party library that is used with different coding guidelines may make extreme pain in doing that object code verification. We've seen the extremes on rewriting yourself, because the cost of performing the verification activity outweighs the redevelopment cost following your own coding guidelines, or adopt a library that is safety critical design from the beginning. Would you agree with that?
Yes.
There's another question about the example. It says, in the example with the remainder function, it seems like the values used cause the divmod function call rather than the programming constructs used. How do you take this into account during the compiler verification? I'm not sure I understand this question. Do you understand what it means?
Not fully, but I can certainly answer the second part of it, in that, yeah, compilers may perform optimization, but they may try and figure out the bounds of certain variables, and they may use that information to perform additional verification. So the answer is that will make compiler verification activity harder. It's something that you would have to test for and check that isn't happening.
Okay, thank you very much. There's another question. It says, I am running a DAL A project, and we are using 100% object code coverage to meet the objective. What should I do? Well, hopefully we said about 12 times, 13 times during the session. Unfortunately, in a naive, simplistic way, this is not correct. If a whole set of conditions apply, then that would be okay. But it's either you need to perform a compiler verification activity, or you need to perform a sampling object code to make sure that the compiler has not introduced code, that then you need to write extra tests for it. Anything you want to add to that, Matt?
No, yeah, or just ultimately talk to your DER. We are not the police when it comes to what you can get away with. There are other circumstances that may permit other methods. You may be doing something in addition to measuring your object code coverage in order to meet that objective.
What we're seeing is that DERs have a very difficult job because they need to be experts on everything. Every single nitty-gritty detail of how to satisfy the different objectives, plus understanding the bigger picture of the process. So the fact that a DER may accept an argument, it doesn't mean that that argument of approach is still correct. Remember, the objective here is to write safe software that doesn't kill people, rather than just, oh, I just need to get a pass on the certificate, even though we know that this software is not correct. And unfortunately, issues of quality in safety critical design that is happening with the current incidents that have been on major aircrafts has shown that a culture of safety from everything we do is essential in our industry. So luckily, nobody has been killed recently, but be close, too close. A few more questions to finish off. What optimization level should I use for my compiler? Mm-hmm. How long is a piece of script?
Yeah, well, the answer is for this objective, 0, no optimization. Because compilers really like to eliminate branches, because branches are terrible for performance, because if the CPU mispredicts the branch, you have to throw away your entire pipeline. And modern processor performance is heavily dependent on branch prediction and deep pipelines because of how slow memory is. So the compilers will try really hard to eliminate branches. And every time they eliminate a branch, well, then you've got object code that no longer traces to your source code. But it's a trade-off, because lowering the optimization level will make your object code verification easier. It could make your worst-case execution time analysis harder, because you've got less CPU overhead to do computation within the deadline. So it's a trade-off between those two activities.
We've seen so many times is that there is no such a thing as the solution. It really depends on the complexity in your software, the amount of resources available, the complexity of your algorithms, and therefore what parts of the code requires performance and what parts of the code requires predictability. We had some customers that said, we cannot afford anything less than -0.2. We know that we'll need to pay the price for doing a lot of extra verification activities later on, but their optimization or their performance, worst-case execution time calculations to fit within the budget or the timing requirements requires that level of optimization. If you can afford not to, a lower level of optimization may introduce less overheads. Sorry, may introduce more traceability from object code to source code, and makes the application of this verification objective easier. If that makes any sense. Mm-hmm. There were another couple of questions. One says, is it true then that for a verified compiler in conjunction with a known set of options that guarantees no new object code, then you do not need to prove object code correctness? Well, there's a lot of things that we need to address here. So first part of the statement says, is it true then that for a verified compiler, such a thing doesn't really exist? We know some cases, on some limited compilers that have some quality, but you cannot qualify a compiler in the general sense, a TQL1, and you can only do that if you actually develop it as it was a DAL A. So what you cannot qualify a compiler, you do a compiler verification activity for the constructs that you're using for your particular system. So the qualifier here is that you verify the compiler for the subset of your using. Okay, that's number one. In conjunction, second part of the sentence says, in conjunction with a known set of options that guarantees no new object code. That is really the right approach. Well spotted means as part of your compiler verification, you first try a few set of compiler options that would, by construction, generate this one-to-one mapping and limit the amount of, or remove completely the amount of extra object code. So that means that the output, you still need to do the compiler verification activity, and therefore the result of that compiler verification, it says, my compiler with these options on this known set of coding constructs, which is the only ones I use, doesn't generate additional code that has matched to the source code. Therefore, I don't need to do anything else. That's correct. You don't prove object correctness, you demonstrate. We are a bit peculiar on use the terminology. Proving something is more like a mathematical notion, but I must to verify that the object is correct. But indeed, you do not need to verify that the additional object code is correct because there's no additional code to verify. So the other part of this question is, you only need to do this once. For as long as you choose the compiler version, and compiler options, and you follow the compiler guidelines, once this is fixed, then this activity can be, you don't need to do it again, unless you change the compiler, or you change the compiler options, or change the compiler version. Okay, anything else you want to add on that?
Well, just that ultimately you either have to make a convincing argument that you have verified this additional object code, or you make a convincing argument that such code, you've eliminated it by these other processes. And ultimately, again, the DER decides whether your argument is convincing, whether you've done enough work, or they may make you go back and do additional work.